It is my great pleasure to announce our next LiDAR panel, which is going to be moderated by Gavin Schrock, and it is Michael Sitar from RIEGL and Katie Fitzsimmons from Hexagon. And we're very excited to use the tech from, have the opportunity to use the tech from both of these companies. And with that, Gavin, I'll turn it over to you.
Yeah, thank you, Chris. And I was just looking at the EA merchandise. So I'm looking for the Scan the World, Save the World shirt. So I'll work on that.
That's gonna, I'm writing that down right now. That's gonna be coming up.
Yeah, and thank you. This is a good follow on to the previous session. The voxels and data cubes is fascinating. But the talk of reality capture is somebody has to capture the reality. So I'm happy to present this session on LiDAR technology for the next 40 minutes. We're going to talk about the practicalities of the tools, of how to do it. There's a session at 3 p.m., which is a great dovetail into this, Ron Chappell and Juan Carlos Diaz, and they're talking about the real world practicalities of doing large scale or large region airborne laser mapping in the Amazon basin. So when Chris put this conference together, I thought of it as like, this is just a really large project, you know, scan the Amazon. Who would need to be the brain trust you would want to have in a room discussing how to do it? And I was really glad that there's a session that's invited two of the leading providers of airborne LiDAR technology. I hope I don't get in trouble for saying I think the two leading outfits. We have Michael Sitar, who's the division manager of airborne laser mapping with RIEGL, and Katie Fitzsimmons, the business development manager with Hexagon, Leica Geosystems, that whole family, but kind of better known for your past roles, directly involved with LiDAR and single photon LiDAR with Sigma Space. So we'll start off with Michael. They'll have short presentations each, and then we'll go into a Q&A session towards the end. So Michael, take it away.
Thanks, Gavin. It's my pleasure to be here. We're looking forward to participating as a company with this worthwhile endeavor. Now, in the famous words of the Greek philosopher Heraclitus, there is nothing permanent except change. And as you look through these images, many of you have had the privilege of seeing some of these natural wonders for yourselves. For the rest who have not, you likely never will, because some, in fact, have been lost forever. As the saying goes, change is permanent. Very recently, just last month, Darwin's arch collapsed due to natural erosional processes. And Malta's Azure window was lost during a heavy storm in March of 2017. However, for some, there still may be a future, despite rising oceans and disappearing shorelines, or deforestation pressures from local governments and populations. The time to act is now. An important step is the mapping and analysis of the Earth as we know it. A record of the present, an inventory of what is and what isn't, but at a resolution and detail that can provide additional physical and chemical analyses that may not be possible from satellite-based imagery alone. The Earth Archives has identified LiDAR as a key technology to map, document, and preserve a digital record of Earth's resources and landscapes. A digital record that will start with the mapping of global tropical forests and ecosystems, and in particular, Amazonia, which is a 2 million square mile or 5.5 million square kilometer area of rainforest in a region that is shared with 9 neighboring nations. But what is LiDAR? How is it different from other technologies? What aspects of LiDAR make it an enabling tool for better forest management and decision processes? Well, briefly, there are several types of LiDAR systems available depending on the technology implementation employed. The more traditional approach has been what is now commonly referred to as linear mode LiDAR. This kind of LiDAR sensor uses a laser rangefinder that directs high-frequency laser emissions to a scanning mechanism, and in combination with the forward motion of the aircraft, a swath of ground measurements are recorded. Independent distance measures determined based on the speed of light and, of course, the time for the laser pulse to reach the ground and to return to a receiving device. Absolute positioning of the aircraft or sensor is determined via an onboard GPS receiver, and platform dynamics are modeled using a high accuracy inertial measurement unit to create a trajectory. The trajectory, the independent range measurements, and the angles are combined and translated to a local coordinate reference frame to create a high density, high accuracy point cloud. Now, the advantages of LiDAR include the fact that it is an active sensor. So there's a laser beam, which is being powered. It can be operated day or night. The data is inherently orthorectified. So unlike imagery, there's no topographical or radial distortion to deal with, and it's also inherently three-dimensional. But more importantly, LiDAR includes the capability of multiple returns, providing structural detail in complex environments that's difficult from imagery alone. And algorithms can then be applied to identify or classify various features within the point cloud, such as ground surface, and optionally remove the overlying vegetation to expose the surface topology or objects beneath. More recently, point clouds are being organized, cleaned, and classified without direct user interaction using advanced AI algorithms. And there'll be a lot of discussion on this during this conference. So whether it is machine learning tools requiring training data sets or deep learning processes that adapt to terrain conditions, LiDAR point cloud classification is becoming faster, it's repeatable, and it's more reliable. For forestry applications and large-scale LiDAR data collection, the advent of AI helps reduce the processing burden that can occur post-mission to deliver actionable data faster than ever before. The following animation illustrates the concept of LiDAR data collection in a forested environment and the transition to map product deliverables. And in this video, these aren't apples, these are supposed to represent LiDAR points on the trees. So this is the surface model, and then filtered, and of course the terrain removed, the overlying features removed, and you're left with the terrain surface, and of course the ability to generate map products from that. In this data example, flown in Guatemala, the ground is completely obscured, so we have really no idea what is below the canopy. However, when we classify the data, we can enable man-made structures to become visible that have been hidden for centuries beneath. So RIEGL offers a number of airborne LiDAR scanners depending on performance and density requirements. And for the Earth Archives Initiative, our flagship product, the VQ-1560 Mark IIS, it's a mouthful for words, but it's really the ideal sensor given its high productivity capability and unique dual laser configuration. So the VQ-1560, it's a purpose-built sensor for wide area mapping, especially for forestry and jungle applications. It incorporates two lasers, enabling a simultaneous double pass over the terrain. And this two-channel configuration results in two matrix point patterns that are then interleaved, canted, and rotated to maximize canopy penetration success. And energy density, of course, within the laser footprint is also critical to ensuring there's enough oomph to reach the depths of the jungle floor and back to the aircraft. So higher energy densities correlates extremely well with canopy penetration success. Now, full waveform analysis is extremely valuable for ensuring true ground detection in dense understories, particularly low-lying vegetation where the ground is often obscured and pulse separation distance are not sufficient to discriminate. So full waveform also provides additional metadata attributes which can be used for improved classification results than what might otherwise be possible using morphological information alone. However, the reality of jungle surveying can quickly temper your productivity expectations. Cloud cover and precipitation events are a constant barrier to collection in tropical environments, often limiting collection altitudes to sometimes less than 2,500 feet and as low as maybe even 1,500. And similarly, atmospheric visibility can be extremely limited, further degrading laser propagation and energy density in the the laser footprint over ground. So if flying low is a necessary requirement to move collections forward, then an alternative might be the use or the consideration of RIEGL's VQ1560 DW. And in this case, this multi-wavelength sensor contains both an IR and a green laser channel. Because vegetation heavily absorbs in the green, operational ceilings are typically much lower anyways. But the spectral information content from the scanner has been demonstrated to provide additional input for things like species classification or discrimination in combination with the LiDAR's traditional high-density 3D structural information. Now, there's a lot of considerations when it comes to jungle surveying and the Earth Archive's first initiative here. I mean, traditional RTK survey practices deploy a GPS base station for differential processing and solution accuracy improvements. However, this can be very difficult to do in many remote regions, and the logistics of doing so are costly. It also restricts operations to a local geographic area proximal to the base station. And when trying to navigate cloud banks, mission flexibility is critical. Now, precise point positioning removes the necessity of a base station and uses the availability of precise ephemeris data after the flight to solve for receiver clock errors and other inaccuracies that are otherwise contained in the raw GPS or GNSS observables. PPP has been around as an alternative for remote sensing or remote surveying using kinematic systems for over a decade now. More recently, an alternative approach, which will also be discussed during this conference, is that which removes the wait time for precise ephemeris data to be made available, but also improves overall accuracy further. And that is the Planex's post-processing RTX solution. Now, all RIEGL sensor solutions come standard with an OEM GNSS INS components from a Planex. In doing so, we were able to leverage the benefit of Trimmo's Centerpoint RTX solution, which is a subscription-based service that is broadcast over satellite L-band or the internet. With the Planex's POSPAC MMS software for high-accuracy trajectory processing of remote surveying applications. And this is invaluable for areas where GPS base stations are difficult or impossible to deploy. But with the added advantage, there's no need to wait for the precise ephemeris info hours after landing like there would be with the PPP solutions. And there's no restriction to GPS baselines. So a very timely technology for executing on these remote areas. Now, other considerations when surveying remote locations include aircraft fuel availability, Jet A versus avgas. So depending on availability, you may actually have to truck the fuel in. This has been the experience of many LiDAR operators that are operating in the Southern Hemisphere. Local airports means the relative locations are typically of greater distances, longer transit times to the project site. And of course, and very importantly is weather and seasonality, dry versus wet. In Amazonia, wet actually equals flooded. They get about 12 feet per year precipitation in this region, translating to over 200 rainy days. And in many cases, water levels are often 20 feet higher during the wet season versus the dry season. Now, 60% of the total rainfall actually occurs during the wet season, which means there's another 40% during the supposed dry season. And so, things like time of day, cloud height ceilings can be severely limiting to data collection. So that time of day collection becomes imperative. So maybe it's best to survey mid-morning ahead of the evening rain showers and after the clouds perhaps have dissipated in the valleys. Infrastructure to support infield processing can also be limiting. At a minimum, coverage and quality must be determined. Data is generally shipped, uploaded back to the office for final processing and information extraction. And of course, this takes time. Is there an opportunity for onboard processing where final map products can be uploaded instead?
Hey, Michael, you have about 3 minutes.
No problem. And sensor configuration. Peripheral imaging sensors provide immense value as well. So what is really the scope of an endeavor such as this? Well, based on sensor performance and nominal point density of 8 points per square meter, say raw data volumes can range from 100 to 200 gigabytes per hour, LiDAR only. And actual volume is a function of target complexity therefore the number of measured returns from a single outgoing mission. Being a vegetated environment in this scenario, we'll assume the worst. Now, the total area of the Amazonia Basin is over 7 million square kilometers, of which I mentioned 5.5 is rainforest. And for this model, we'll assume the entire basin. So if we consider an aircraft speed of 160 knots and altitude of 7,000 feet, then the area coverage rate is about 230 square miles an hour, or 570 square kilometers when accounting for side lap. So this equates to about 500 days of laser on time, 1,540 survey days, using 8 hours per day, or 4.2 years if we're talking about a single sensor. And that's without taking into account things like transit, turn times, control strips, weather, and cloud heights. And then you translate that to data volumes, and we're looking at almost 3 petabytes of raw data collection and even more of the full waveform. On the processing side, RIEGL scanners utilize a processing wave platform called RIProcess. Till recently, software modules were licensed as individual add-ons. And with the recent refactoring to 64-bit architecture, the software now amalgamates many of these modules, resulting in faster processing speeds, reduced file sizes, improved software organization. And on the processing side, RIEGL scanners provide efficiencies that can be demonstrated in terms of the output speeds that are 3 times faster than the previous release. And basically, this increase in processing efficiency is critical to keeping up with the performance increases of the sensors themselves, especially as it relates to higher laser pulse rates. And so in summary, airborne LiDAR data collection, it's not without its challenges. It's a significant endeavor requiring significant resources. But we have the tools, and the question really is, are you up to the task?
Okay.
Thanks, Gavin.
Yeah. Thank you, Michael. Katie, stick around for questions, and then I assume you'll be in the networking rooms afterwards as well. Katie, you have the floor, and looking forward to hearing a bit more about single photon LiDAR.
Perfect. I think, Michael, you just have to stop sharing so I can go ahead and start sharing. Thanks, everybody, for having me this afternoon to participate in the Earth Archive. As Gavin mentioned and alluded to, I had spent about 10 years with Sigma Space, which was the firm that developed and then commercialized the single photon LiDAR technology before we were acquired by Hexagon a few years ago. So to set things up today, I wanted to give you a quick overview of kind of the overall product portfolio inside of the Hexagon or Leica Geosystems division, and then also speak a little bit more to why the single photon LiDAR technology specifically is a really good solution when we're looking at wide area coverage. So let's get started. You'll see the first sensor here that we mentioned is our Citymapper 2 sensor. And I'd say over the last maybe decade or so, one of the big shifts we've seen in the LiDAR and aerial imaging market is bringing these two technologies together. So when you're in the air, you're maximizing collection for both data sets as much as possible. And that's what this first sensor does here. The Citymapper 2 collects high resolution ortho images, at least 10 points per square meter on the LiDAR, and oblique images as well. The next two sensors here, the DMC3 and the ADS-100, these sensors have been flying and capturing imagery across the world. Likely millions of square kilometers have been captured since these two products were brought into the market. Next, we have our two topographic LiDAR sensors, the SPL-100 and the Terrain Mapper 2 sensor. Michael alluded to this a little bit in his presentation, where our Terrain Mapper 2 works in a linear mode regime, whereas our single photon LiDAR SPL-100 works in a single photon detection regime. And that's really the big difference between those two sensors. Both of them also fly with context imagery sensors, so you're always picking up the LiDAR data as well as the imagery data as well. And then certainly we offer a couple of bathymetric LiDAR sensors. So if you're looking for coastline, rivers, streams, lakes, that type of thing, those are the best sensors you can use to grab what the Earth's surface looks like under the water. Now, of course, capturing the data is one big component of the mission Earth Archive has laid out, but getting that data processed to a usable state is something that is equally important. And as you can see on the right there, through our unified processing tools, you're able to create in a pretty quick way ortho images, LiDAR point clouds, digital elevation models, bathymetric point clouds. So the entire data stack that is filtered, not yet classified, but pretty much ready to go. So let's jump in and talk a little bit more about this single photon LiDAR technology and what makes this technology fairly unique. Our biggest difference is rather than sending out a single beam or single laser beam of energy for acquisition, we're able to take that large energy laser beam and using a diffractive optical element, break it up into a 10 by 10 array of what we call laser beamlets. And actually you can kind of see an imposed image there on the scanner surface of what that 10 by 10 arrangement looks like. That is then scanned conically around the scene. So you're going to get 2 looks at every spot on the ground, a look from the forward part of the scan and then the aft part of the scan. And then as those returns come back to the LiDAR sensor, each of those laser beams is attached to a single detector element or an array of detectors. The detector we use has an ultra fast recovery time, which allows an infinite number of returns to be recorded. So actually our technology is quite similar to that of linear mode technology. And one of the best ways to almost understand it is if you had 100 linear mode sensors working right next to each other, that's what the single photon LiDAR sensor ultimately ends up doing for you. And this is really where we gain our efficiency and our optimization of time in the air. Also, because we're firing so fast, we're collecting a lot more points per unit time. So we're firing up to 6 million points per second, which gives you higher resolution, higher point density data as we scan across the scene. A couple of other items to note on the sensor. You can see there's an adjustable wedge scanner here. So this can give you a field of view for up to 40 degrees if you're maximizing acquisition, or you can narrow it into, say, a 20-degree field of view if you're really looking to maximize point density. I mentioned there's a medium format camera that flies alongside the LiDAR, again, for context, but also for imagery use. Our system does fly at 532, and Michael had mentioned this in his program with his sensor flying on dual wavelengths. Our selection of the green wavelength was really based on where our detectors are optimized, and that just happens to be in the green. Our system has been demonstrated over a number of projects to deliver very accurate data, so less than 10 centimeters in the z-axis. And as I mentioned, because of the high speed of our detectors and their recovery time, we can collect multiple returns per pulse, which gives you that ability to collect data at the top of the canopy, the understory, and then certainly the forest floor. We take a quick look at productivity here across the Leica Geosystem sensors. You can see starting on the left with our city mapper sensor, as the name kind of alludes to, this sensor is built for city modeling, smaller projects, high fidelity projects, projects where you need super high resolution or point density in order to fulfill a certain requirement. This sensor isn't really built for acquisition maximization. It's built to get you a lot of data. The next sensor, also a linear mode sensor, the Terrain Mapper 2, flies slightly higher, around 6,000 feet AGL, and can collect up to about 450 or so square miles of data per hour and deliver about a 10 point per square meter product. So still looking at a really great QL1 product, but when you really need to cover the amount of area that the Earth Archive has goals and to cover, you have to look at something slightly different. And this is where the SPL 100 comes in. Capabilities of collecting about 250 square miles of data per hour, a 9,000 foot swath, and we're flying at altitudes around 12,500 feet. This is where you really start to maximize how much data you can go collect in a single day or a single mission set. Now, it sounds like there's been a lot of conversation about data processing, data workflows. How do we use this data and then get it out to our stakeholders? And similar to the RIEGL data processing, our team comes with a workflow known as HexMap that is able to take all of your raw data from your imager, your LiDAR sensor, the GPS IMU data, and then take it from that raw spot to an end product. And here you can see we've built in LiDAR noise filtering, which specific to the SPL 100, given that it's a green system, is susceptible to quite a bit more noise than those that fly at 1064. So we've built in all of that noise filtering and noise removal regime, LiDAR calibration, registration, and then again, if you're flying with an imager as well, you're getting that data co-registered, so it's you're seeing it at the same spot on the ground. And then, of course, product generation. So this is what everybody is interested in getting their hands on. Either it's imagery or point clouds, digital elevation, digital surface models. And then when you're looking at a sensor like the City Mapper, you start to build out meshes and other really amazing kind of virtual 3D models, which are pretty neat and fun to look at. I wanted to kind of set up a little bit of context for what these large scale programs look like. So while the SPL doesn't participate in the Hexagon content program, the Hexagon team does run a fairly large imagery program. We have a library of imagery of the United States, parts of Western Canada, and then parts of Western Europe that we've been running since 2014. In order to keep just those areas updated on an annual basis, and we're not even updating all of them, it requires a fleet of 20 to 30 aircraft and sensors. Data processing, you can see some of the numbers here, over 600 terabytes of raw data collected just in 2020. And I think that, the 4 petabytes of networking storage, this not only holds kind of our working library, but then all the storage requirements that kind of peak as we're processing data. This is all to support about 5 locations across the world that help support all of our data processing. Now, from a single photon LiDAR sensor availability, we have 7 active systems right now that are flying a variety of projects across the world that could certainly help contribute to the goals that the Earth Archive has laid out. So I wanted to walk through a couple of projects that we are either actively engaged with or that we've been working on to give you a little bit more context and ideas of what the single photon LiDAR is capable of. So one of the largest projects, and probably maybe most akin to what we're talking about in the Amazon, though the tree structure is quite a bit different, is with the Ontario Ministry of Natural Resources. This is a multi-year project to collect 500,000 square kilometers of data at 25 points per square meter. So it's a very high fidelity project. They had previously flown all of their areas of interest with linear mode LiDAR systems, and they knew that if they wanted to get a higher point density product within the same timeline that they had used previously, they had to go with a single photon LiDAR system. So to date, we've collected nearly 150,000 square kilometers of data. Over 1,000 flight lines have been flown. And this is, in fact, right now, kind of the prime season for the OMNR work. This is, as you can imagine, something that is supporting forestry and land use monitoring, so that we need to fly in a full leaf capacity. That gives us a timeline of approximately late May to early September to fly as many square kilometers as we possibly can. Typically, May and early June are our best flying times. So we've got 6 aircraft up there right now flying, and as long as the sun's out, we are up there collecting data. The next opportunity I wanted to talk about was done in conjunction with NOAA and our friends at USGS and Wolpert to map the Big Island of Hawaii. This was quite interesting to many of you on the call because this canopy structure and certainly terrain may be the most similar that we've got here in the US to something down in South America. We were looking at delivering a QL1 or an 8 point per square meter product and ended up delivering about 15 points per square meter. This is a good testament, though, to the challenges that the climate and the weather can do for a LiDAR project. As you can see, only about 4,000 square miles to collect the island, but it took us about 3 years to get it done. And that was due to the variety of climate zones, the way we had to flight plan. Elevation change was upward of 13,000 feet across the island. So flight planning, I think, probably took a lot of engineering thought, maybe more than flying over something a lot easier. But this was what you can see here on the left is a 1 meter DEM of Mauna Kea, the volcano there. And this data ended up being just gorgeous, beautiful data. And we were really excited to support NOAA, USGS, and Woolpert on this one. The next project is much smaller, but a little bit closer to where our targets are, at least for the first part of the Earth Archive in Guyana. As part of an effort to update their nationwide DEM, we did a small pilot project, just under 1,000 square kilometers, to collect a few areas in Guyana. And again, some of the challenges that Michael was just describing about working in countries, certainly we felt those effects. Being able to find a good base station, getting equipment in and out of the country turned out to be quite challenging. Plus you're dealing with the weather. And so all of those things combined, I think that just having a single sensor, a single crew on the ground made it quite challenging to be able to get as much data as possible, even when you had good weather. Now, I think it's worth mentioning that the SPL has a big sister, the SPL-100HA. This was a custom development that Sigma Space did for a US government customer. This sensor is built for efficiency and speed. She flies at about 25,000 feet, 200 knots, and collects about 8 points per square meter. Most notably, and something that I think I'm feeling some pride for, is that they were able to collect about 50,000 square kilometers of data in just 30 days. They had a stretch of really amazing weather and just could knock out loads and loads of flights. And that was kind of the outcome. Interestingly, these guys turn data around in 24 hours. So they've got to be able to produce data products to deliver to their end users very, very quickly. So it just goes to show you that the SPL-100HA flying at kind of the commercial altitudes, 12,500 feet, or even at these higher altitudes in areas where weather is maybe not such a concern, both of those things are capabilities the SPL has demonstrated. And then finally, many of you probably know about this, but NASA's Icesat-2 mission actually is a single photon LiDAR mission. All of the timing electronics used in the Atlas sensor, which is the laser altimeter aboard the Icesat-2 mission, is in a photon counting regime. So all of those electronics were developed at Sigma Space, and the Icesat-2 was launched in 2018 and has been doing an amazing job collecting data. And while the mission, and I think that one of the speakers previously had mentioned, the common mission to be able to kind of see polar ice cap change. What I think that the ISAT team found is that they were getting a lot more data outside of just the polar ice caps. For instance, you can see here, this is a much more tropical region, and the cross section in the bottom of that image there, the z-axis has been, or excuse me, the x-axis has been condensed quite a bit. But you see you're getting a nice elevation model of the trees. You see a beautiful ground, and then you're even picking up some of that shallow bathymetry as you're coming across that barrier island. Just like the SPL-100, the Icesat-2 flies at 532 nanometers in the green wavelength. They're collecting a measurement about every 70 centimeters. I think what's probably most impressive about this sensor is that they're seeing around a 3 centimeter vertical accuracy, which is really just incredible and a testament to the team who worked on that. So just a quick conclusion, I think that, Hexagon and the Leica Geosystems team, Leica just celebrated their 100-year anniversary last year. We have a long history of supporting airborne imaging and airborne LiDAR missions to accomplish these really exciting and big projects. You're going to have to use some pretty innovative and next generation technology, and the single photon LiDAR definitely would fit the bill for that. And as you've already been discussing, acquisition, data processing, storage, and then ultimately data dissemination, right? That's what we're all in for. But all of those things kind of have to be thought through and taken into account. So with that, I can wrap it up. And Gavin, hand it back over to you.
Okay, yeah. Thank you, Katie and Michael. We only have a few minutes for questions. There's a whole bunch. I'm going to encourage people to go over into the networking lounge, look in the chat box, and you'll see a link there to sign up and go into that. But I got to grab a couple of the questions. It's the Amazon is diverse in a lot of ways. There's lots of areas of interest besides the vegetation. There's the built natural environments. There's probably be a mix of sensors used. Strengths and weaknesses to the various types, single photon, linear, and Geiger, even that, and you've got variations in the linear. For instance, like Michael, what would be advantages of a linear at a low altitude, considering the Amazon, nature of the Amazon basin?
Well, thanks, Gavin. I think one of the biggest challenges, and Katie had acknowledged this as well, especially in Hawaii, is the amount of clear days that you can actually fly. This is the reality of these environments. And so with those types of challenges, the advantages of linear mode LiDAR is you can get low, you can get those high densities that are required. But more interestingly, it's a discrete type of measurement system, right? You have independent range measurements for every laser pulse. And in doing so, with the scan geometry, you can really get underneath those trees and get different view perspectives through the canopy to get down to the ground. And that's really the essence of trying to fly these areas, is to get that ground data. And of course, if you can't see the sky beneath the canopy, then there's chances the LiDAR is not going to make its way through either. So some of the flexibility associated with the linear mode LiDAR system configurations and those application-specific scan geometries and feature sets have been developed over years of field trials and practical operations.
Okay, quick question about atmospheric noise and false positives in a highly humid place. Katie and Michael, would better meteorological information on the ground, like the microburst profiles, help you in processing to mitigate that, or are you pretty much just have to choose the weather conditions for the most optimal flights?
Yeah, that's a question that comes up a lot, right? The reality is sensor manufacturers push the envelope of performance with higher laser output power, increasing detection sensitivity, but also higher sampling rates. Then the near field returns can start to make their way into the data, and especially these human environments that you mentioned. And this is particularly the case when operating in a multi-pulse environment with the linear mode LiDAR systems, where the near field returns can start to be pushed into the ground data, which makes them difficult to remove. And there's several approaches that can be considered. A popular one is a post-processing effort where they, as Katie mentioned, running spatial filtering algorithms to remove the isolated points. This has been successfully implemented in AI-powered algorithms, so a lot of that is automated. And another way, which is what RIEGL's done as well, is to try to address that at the source, at the front end of collection to minimize them. And we've developed what's called an atmospheric clutter suppression filter that looks at those near field returns and adjusts things like receiver sensitivity based on the strength of the returns near the receiver. So I think in combination of looking at meteorological conditions, but I think the very reality of even in clear skies, that humidity environment, that there needs to be an emphasis placed on at the front end of the hardware of collection, but also on the post-processing to minimize that type of data.
Okay, we have to wrap it up. Thank you, Michael. Katie, I have you got 20 seconds to answer.
Yeah, go for it.
The question is the Guyana, you came out with about 2 points per meter. Would you expect that over much of the Amazon basin, with vegetation and humidity and things being similar?
Yeah, I think that for the Guyana project, that project was spec'd out and then planned to achieve a certain point density. When we're looking at achieving higher point densities, like for example, with the OMNR project in Canada, our flight planning plans to achieve more than 25 points per square meter. And that's given all of the canopy structure that we're facing. So yeah, I think that a lot of it depends on what the goal of the project looks like in Guyana, because it was only 2 points. It is going to be quite a bit harder to see a really beautiful surface when you're only picking up 2 points a square meter, because most likely those points are going to be falling in the trees.
Okay. we're wrapping it up, handing it off. Michael mentioned about the GNSS, you know, in the control. There is a session at 3:30 today specifically on that. I got to hand this back. Thank you both.